In this lesson, you will learn what is big data. Understand and explain the concept of Hadoop and MapReduce technology for big data processing. And understand why big data analytics is important.
Welcome to another video from explainingcomputers.com. This time I'm going to talk about big data. This is the next big thing in computing and generates value from very large data sets that cannot be analysed with traditional computing techniques. The quantity of computer data generated on planet Earth is growing exponentially for many reasons. For a start, retailers are building vast databases of recorded customer activity. Organisations working in logistics, financial services, healthcare and many other sectors are also capturing more data. And public social media is creating vast quantities of digital material. As vision recognition improves, it is additionally starting to become possible for computers to extract meaningful information from still images and video. As more smart objects go online, big data is also being generated by an expanding Internet of Things. And finally, several areas of scientific advancement are starting to generate and rely on vast quantities of data that were until recently almost unimaginable. Big data is often characterized using the 3 V's of volume, velocity and variety. Here, volume poses both the greatest challenge and the greatest opportunity, as big data could help many organizations to understand people better and to allocate resources more effectively. However, traditional computing solutions like relational databases are not scalable to handle data of this magnitude. Big data velocity also raises a number of issues, with the rate at which data is flowing into many organizations now exceeding the capacity of their IT systems. In addition, users increasingly demand data that is streamed to them in real time, and delivering this can prove quite a challenge. Finally, the variety of data types to be processed is becoming increasingly diverse. Gone are the days when data centers only had to deal with documents, financial transactions, stock records, and personnel files. Today, photographs, audio, video, 3D models, complex simulations, and location data are being piled into many a corporate data silo. Many such big data sources are also unstructured and hence not easy to categorize, let alone process with traditional computing techniques. Due to the challenges of volume, velocity and variety, many organizations at present have little choice but to ignore or rapidly excrete large quantities of potentially valuable information. Indeed, if we think of organizations as creatures that process data, then most are rather primitive forms of life. Their sensors and IT systems are simply not up to the job of scanning and interpreting the vast oceans of data in which they swim. As a consequence, most of the data that surrounds organizations today is ignored. A large proportion of the data that they gather is then not processed, with a significant quantity of useful information passing straight through them as data exhaust. For example, until recently, the majority of the data captured via retailer loyalty cards was not processed in any way. And almost all video data captured by hospitals during surgery is still deleted within weeks. Today, the leading big data technology is Hadoop. This is an open-source software library for reliable, scalable, distributed computing and provides the first viable platform for big data analytics. Hadoop is already used by most big data pioneers. For example, LinkedIn currently uses it to generate over 100 billion personalized recommendations every week. Hadoop distributes the storage and processing of large datasets across groups or clusters of server computers. Whereas traditional large-scale computing solutions rely on expensive server hardware with a high fault tolerance, Hadoop detects and compensates for hardware failures or other system problems at the application level. This allows a high level of service continuity to be delivered by clusters of individual computers, each of which may be prone to failure. Technically, Hadoop consists of two key components. The first is the Hadoop distributed file system, which permits high bandwidth cluster-based storage. The second is a data processing framework called MapReduce. Based on Google's search technology, MapReduce distributes or maps large datasets across multiple servers. Each server then creates a summary of the data it's been allocated. All of this summary information is then aggregated in the so-termed reduce stage. MapReduce subsequently allows extremely large raw datasets to be rapidly distilled before more traditional data analysis tools are applied. For organizations who cannot afford an internal big data infrastructure, cloud-based big data solutions are already available. Where public big datasets need to be utilized, running everything in the cloud also makes a lot of sense, as data does not have to be downloaded. For example, Amazon Web Services already hosts many public datasets containing government and medical information. Looking further, quantum computing may greatly improve big data processing. Quantum computers store and process data using quantum mechanical states, and will in theory excel at the massively parallel processing of unstructured data. As IBM explain, big data provides an opportunity to find insight in new and emerging types of data. Or as Oracle put it, big data holds the promise of giving enterprises deeper insight into their customers, partners, and business. In time, big data may also help farmers to accurately forecast bad weather and crop failures. Meanwhile, governments may use big data to predict and plan for civil unrest or pandemics. In a recent report, the McKinsey Global Institute estimated that the US healthcare sector alone could achieve $300 billion in efficiency and quality savings every year by leveraging big data. Across Europe, they also estimate that using big data could save at least $149 billion in government administration costs. In March 2012, the US government announced a $200 million investment in big data projects. By the end of 2015, Cisco estimate that global internet traffic will reach 4.8 zettabytes a year. That's 4.8 billion terabytes, and indicates both the big data challenge and the big data opportunity ahead. More information on big data can be found on explainingcomputers.com. But now that's it for another video, and I hope to talk to you again very soon.
Banks face many challenges as they strive to return to pre-2008 profit margins. These challenges include reduced interest rates, instability in financial markets, tighter regulations, and lower performing assets. Fortunately, banks taking advantage of big data and analytics can generate new revenue streams with personalized offers, targeted cross-sell, and improved customer service. Big data and analytics provide more insight by analyzing a higher volume and variety of data types from more sources than ever before. Deeper insight by digging deeper into customer information and behavior, enabling segment of one marketing. And faster insight by performing real-time analysis of customer information to deliver offers at the point of decision. Big data and analytics can analyze many types of customer information, including spending patterns, behavior, channel usage, product portfolio, bank interactions, credit information, social media, and customer profitability. Here's a day-in-the-life customer scenario as an example of big data and analytics in action. Peter is a customer of leading bank with a mortgage, checking and savings accounts, and a line of credit. Peter is remodeling his kitchen and decides to buy a new set of chef knives. The bank recognizes that Peter has made a number of household purchases lately and analyzes his financial and transactional data, including spending patterns, income, savings balance, available credit, loans, credit score, and level of risk. The bank also analyzes his related activity on social media and learns that Peter loves to cook. He enjoys gourmet restaurants. He blogs about his dining experiences and indicates he likes a new restaurant-style gas stove. Using big data capabilities and predictive analytics, the bank anticipates similar home purchases, but knows that Peter is nearing his credit limit. The bank wants to seize this business opportunity before Peter is offered a credit card from a retailer. The bank sends Peter an offer to extend his line of credit. He uses the additional credit to buy the professional-style stove for his kitchen. The banking system also identifies this as a large purchase and prompts Peter to take and archive a photo of the receipt and warranty. As well, the system recognizes this as a home appliance purchase and offers an extended warranty to Peter based upon his zip code. It's now 11:30 a.m. Analyzing Peter's regular lunchtime purchase behavior and preferences, the bank sends him a personalized offer from one of leading bank's nearby merchants, Chefwich. The system prompts Peter to share the offer with his friends through social media. As Peter pays his bill, the bank sends an alert to verify that he has authorized the purchases made today, preventing fraudulent charges to his account. Later, Peter logs into his account with his tablet computer. He looks in My Offers to find his personalized offers. After analysis of his spending patterns, the bank suggests that Peter sign up for their Smart Sweep service. Peter also sees a home equity line of credit offer based on an analysis of his financial condition as well as information on his home from third-party sources. Finally, the bank recommends that Peter sign up for overdraft protection to avoid the frustration of any future fees. While Peter is logged into his account, he also views the Spending Manager feature to gain insight into how his spending changes from month to month. Peter can compare his spending to financial peers in his geographic location, income, and age bracket. With new capabilities provided by big data and analytics, banks can develop new products and services that help customers manage their finances and save them money, deliver relevant services and offers that fit seamlessly with customers' daily lives, improve the customer experience, and promote customer satisfaction and retention, and at the same time, generate new streams of revenue for the bank.
What is a big data? It is about capability to manage a huge volume of disparate data, at the right speed, and within the right time frame to allow real-time analysis. It is typically characterized by the 4 V's: volume, velocity, variety, veracity. Volume. The benefit gained from the ability to process large amounts of information is the main attraction of big data analytics. Having more data beats out having better models. If you could run that forecast taking into account 300 factors rather than 6, could you predict demand better? This volume presents the most immediate challenge to conventional IT structures. It calls for scalable storage and a distributed approach to querying. Many companies already have large amounts of archived data, but not the capacity to process it. Definition of size of data. Growth of big data and market. 90% of the data in the world has been created in the last 2 years alone. Unstructured data will account for more than 80% of the data collected by organization. Velocity. The importance of data's velocity. The increasing rate at which data flows into an organization has followed a similar pattern to that of volume. Example, the smartphone era has huge impact on the increasing demand for data streaming as information on demand increases. Organization that can provide fast response to information demand tends to have an advantage. Example, mobile banking. The fast velocity flow of information from an organization creates challenges on the need have high computer processing power to speed up information processing. Variety. Rarely does data present itself in a form perfectly ordered and ready for processing. They comes in different forms and formats. A common theme in big data systems is that the source data is diverse, and doesn't fall into neat relational structures. It could be text from social networks, image data, a raw feed directly from a sensor source. None of these things come ready for integration into an application. Veracity. This is a challenge to big data analytics. Veracity refers to the quality of data used for data analytics. Accuracy of data, example, biases, noises and abnormalities in data. Reliability of data source, example, uncertainty of data authenticity, fake news. Context of analysis, example, analyzing the appropriate data sets. What is big data analytics? Big data analytics is the process of examining big data to uncover hidden patterns, unknown correlations and other useful information that can be used to make better decisions. With big data analytics, we can analyze huge volumes of data that conventional analytics and business intelligence solutions can't handle. Consider that your organization could accumulate, if it hasn't already, billions of rows of data with hundreds of millions of data combinations in multiple data stores and abundant formats. High-performance analytics is necessary to process that much data in order to figure out what's important and what isn't. Big data analytics, hence, requires technologies that can support huge volume of data processing within a shortest time and large data storage for different types of data. Hadoop. Hadoop is designed to process huge amounts of structured and unstructured data, terabytes to petabytes. Originally built by a Yahoo engineer named Doug Cutting, Mike Caffarella and team in 2005. And is now an open source project managed by the Apache Software Foundation. Hadoop is designed to parallelize data processing across computing nodes to speed computations and hide latency. Hadoop was developed because it represented the most pragmatic way to allow companies to manage huge volumes of data easily. Hadoop allowed big problems to be broken down into smaller elements so that analysis could be done quickly and cost-effectively. By breaking the big data problem into small pieces that could be processed in parallel, you can process the information and regroup the small pieces to present results. Hadoop has two primary components. Hadoop Distributed File System, HDFS. A reliable, high bandwidth, low cost, data storage cluster that facilitates the management of related files across machines. MapReduce engine. A high-performance parallel/distributed data processing implementation of the MapReduce algorithm.
We've been talking about core Hadoop, which consists of HDFS and MapReduce, but since the project was first started, an awful lot of other software has grown up around it. And that's what we call the Hadoop ecosystem. Some of the software is intended to make it easier to load data into the Hadoop cluster, while lots of it's designed to make Hadoop easier to use. For example, as you'll see in the next lesson, writing MapReduce code isn't completely simple. You need to know a programming language, such as Java, Python, Ruby, or Perl. But there are lots of folks out there who aren't programmers, but can write SQL queries to access data in a traditional relational database system like SQL Server. And of course, lots of business intelligence tools want a way to hook into Hadoop. For that reason, other open source projects have been created to make it easier for people to query their data without knowing how to code. Two key ones are Hive and Pig. Instead of having to write mappers and reducers, in Hive you just write statements like this, which look very much like standard SQL. The Hive interpreter turns the SQL into MapReduce code, which then runs on the cluster. And an alternative is Pig, which allows you to write code to analyze your data in a fairly simple scripting language rather than MapReduce. Again, the code is just turned into MapReduce and run on the cluster. Hive and Pig are great, but they're still running MapReduce jobs, which, as you'll see, can take a reasonable amount of time to run, especially over large amounts of data. So another open source project is called Impala. Impala was developed as a way to query your data with SQL, but which directly accesses the data in HDFS, rather than needing MapReduce. Impala is optimized for low latency queries. In other words, Impala queries run very quickly, typically many times faster than Hive, while Hive is optimized for running long batch processing jobs. Another project used by many people is Scoop. Scoop takes data from a traditional relational database, such as Microsoft SQL Server, and puts it in HDFS as delimited files so it can be processed along with other data on the cluster. Then there's Flume, which ingests data as it's generated by external systems, and again puts it into the cluster. HBase is a real-time database built on top of HDFS. And there's more. Hue is a graphical front end to the cluster. Oozie is a workflow management tool. Mahout is a machine learning library. In fact, there are so many ecosystem projects that making them all talk to one another and work well can be tricky. To make installing and maintaining a cluster like this easier, Cloudera, the company we work for, has put together a distribution of Hadoop called CDH. CDH, or the Cloudera distribution including Apache Hadoop, takes all the key ecosystem projects, along with Hadoop itself, and packages them together so that installation is a really easy process. And the components are all tested together so you can be sure there's no incompatibilities between them. Of course, it's free and open source, just like Hadoop itself. While you could install everything from scratch, it's far easier to use CDH, and that's certainly what we'd recommend. In the next lesson, in fact, you'll be downloading and running a virtual machine which has CDH installed. For more information on the Hadoop ecosystem and how each of these components works, see the instructor notes.
Once upon a time, in a village called Hadoopville, there lived a bunch of people who were called Hadoopians. Hadoopians used to store tons of data with them. Let's see how they used to do this. Hadoopians categorized themselves into two groups. They are called masters and slaves. Masters, in turn, had two responsibilities. They are, number one, to store data, and number two, to run parallel computations on that data. Slaves, on the other hand, simply execute the tasks that their masters ask them to do. These are the guys who get their hands dirty and does all the background work. Among the masters, the one who takes care of the storing of the data is called Mr. Name Node. And the slaves who assist Mr. Name Node are called data nodes. And similarly, the master who takes care of running computations on the data is called Mr. Job Tracker. And his slaves are called task trackers. Let's see further what these guys are really up to. Introducing Mr. Name Node. Mr. Name Node is one of the only master in Hadoopian community who takes care of storing the data in blocks. He takes the help of his minions called data nodes to store and replicate the data. Mr. Name Node employs his special brain and memory called random access memory. In his random access memory, Mr. Name Node practically remembers every single data block and which of his subordinate data nodes are storing that information. Mr. Name Node is considered a very important person in Hadoopian community. If he becomes ill or dies, there is no way to get access to all of the data that is residing with his data nodes. He stores all of the metadata related to a file in his special random access memory. If Mr. Name Node loses his life, the Hadoopian community loses its identity and the data that is stored. Introducing data nodes. These data nodes are the ones who work for their boss, Mr. Name Node, and assist him in storing the data. The actual work of storing the data is all done by these guys. However, Mr. Name Node is the one who remembers which block of data is contained within which data node. The data nodes also have their tiny little special RAMs, but usually they are used to do their own specific tasks. Introducing Mr. Job Tracker. Now he is another master, just like Mr. Name Node. He takes care of processing and computing on the data. He uses a special technique called map reduce. He also has his own minions who does the actual job, and they are called the task trackers. Introducing task trackers. Task trackers are the slaves for the master, Mr. Job Tracker. A huge job is split into many tasks, and each task is assigned to a task tracker by their master, Mr. Job Tracker. Task trackers execute their part and finally report their completion to Mr. Job Tracker. In this way, the Hadoopians executed their respective responsibilities in mutual cooperation with each other. However, none of the citizens of Hadoopville ever directly interacted with the Hadoopians. They always employed a third-party middleman, agents, to communicate. These agents were called as client machines. Introducing Mr. Client Machine. If someone wants to store data with Hadoopians, they have to approach Mr. Client Machine. And the client machine then further gets the work done by communicating with the Hadoopians. So let's say a user comes to Mr. Client and says that he needs to store a 144 MB size of file with Hadoopians. Mr. Client immediately agrees to help, but says that he has to break that file into blocks of size 64 MB. So he makes 3 slices, of which 2 of them are of size 64 MB, and the last one is of size 16 MB. After slicing these 3 blocks, Mr. Client consults with Mr. NameNode for help. Mr. Client requests Mr. NameNode to help store the data, and Mr. NameNode further collaborates with his minions, the data nodes, and gives Mr. Client 3 data nodes where Mr. Client can store the 3 blocks. The data nodes live together in the 3 buildings, Building A, Building B, and Building C. Depending upon the current GPS location of Mr. Client, Mr. NameNode gives the 3 data nodes that he can work with in the increasing order of the distance. In this case, Mr. NameNode replies back to Mr. Client to store the data on A2, data node B1, and data node B3, with data node A2 being the most nearest data node to Mr. Client. Mr. Client then communicates with Mr. A2, the data node, and hands over the first block to store. A2 gladly accepts the data block and stores it on his hard disk. A2 realizes that the replication factor is 3 and hence forwards the copy of the exact same block to the next data node in the queue. In this case, Mr. A2, the data node, directly communicates with Mr. B1 of Building B and hands over the block to copy. Mr. B1 accepts the copy and does the same exact favor of forwarding the copy to Mr. B3, the data node, who lives in the same building as Mr. B1. It's important to note here that Mr. Client never had to communicate with Mr. B1 or Mr. B3. All he had to do was to communicate with the first data node who is closest to him. It is Mr. A2, the data node, who further communicates with the next data node, and the next data node does the same. This entire chain of replication is called replication pipeline. Also, it's important to see how Mr. NameNode did not intervene in the data block replication process, except that he gave the list of the data nodes that the Mr. Client can work with. However, after the data nodes are done with their job, they all report back to Mr. NameNode that they have successfully copied the block 1. With this, Mr. NameNode officially declares that the block 1 of the file has been stored into Hadoop. And he writes this information into his special memory called random access memory. Mr. Client then repeats the same process again for block 2 and block 3. Every time Mr. Client communicates with Mr. NameNode for the address of the data nodes, each time Mr. NameNode may assign a different data node to store each of those blocks. Once all of the blocks are written and replicated in Hadoopville, then Mr. Client requests Mr. NameNode to close the case. Let's talk about HDFS read. Let us say that the user approaches Mr. Client after 2 months and demands that he wants to read his file back. Mr. Client agrees to get the file, but immediately reaches out to Mr. NameNode to ask where to find the blocks that makes up the file. Remember, Mr. NameNode is the only guy who knows this and remembers this in his random access memory. He replies back with the data nodes that store the 3 blocks that make up the file. Then Mr. Client directly gets to those data nodes and asks them for the file blocks. The data nodes give all the file blocks they are storing for this file, and then finally the client stitches all those blocks into a final file and then hands it over to the user. So this is how the HDFS read operation works.
Hadoop Distributed File System, HDFS. HDFS is a versatile, resilient, clustered approach to managing files in a big data environment. HDFS is not the final destination for files. Rather, it is a data service that offers a unique set of capabilities needed when data volumes and velocity are high. Because the data is written once and then read many times thereafter, HDFS is an excellent choice for supporting big data analysis. The service includes a name node and multiple data nodes running on a commodity hardware cluster, and provides the highest levels of performance when the entire cluster is in the same physical rack in the data center. In essence, the name node keeps track of where data is physically stored. Name node. HDFS works by breaking large files into smaller pieces called blocks. The blocks are stored on data nodes, and it is the responsibility of the name node to know what blocks on which data nodes make up the complete file. The name node also acts as a traffic cop, managing all access to the files, including reads, writes, creates, deletes, and replication of data blocks on the data nodes. The complete collection of all the files in the cluster is sometimes referred to as the file system namespace. It is the name node's job to manage this namespace. Even though a strong relationship exists between the name node and the data nodes, they operate in a loosely coupled fashion. This allows the cluster elements to behave dynamically, adding, or subtracting, servers as the demand increases, or decreases. Data nodes are not very smart, but the name node is. The data nodes constantly ask the name node whether there is anything for them to do. This continuous behavior also tells the name node what data nodes are out there and how busy they are. The data nodes also communicate among themselves so that they can cooperate during normal file system operations. This is necessary because blocks for one file are likely to be stored on multiple data nodes. Data nodes are not smart, but they are resilient. Data nodes use local disks in the commodity server for persistence, permanent storage. All the data blocks are stored locally, primarily for performance reasons. Data blocks are replicated across several data nodes, so the failure of one server may not necessarily corrupt a file. As with all file systems, data integrity is a key feature. HDFS supports a number of capabilities designed to provide data integrity, which is managed by using transaction logs, checksum,
MapReduce is at the heart of Hadoop. It's this programming paradigm that allows for massive scalability across hundreds or thousands of servers in a Hadoop cluster. The MapReduce concept, it's easy to understand. The term MapReduce actually refers to two separate distinct tasks that Hadoop programs perform. The first is the map job, which takes input data and processes it to produce key value pairs. The reduce job takes those key value pairs and then combines or aggregates them to produce the final results. As the name MapReduce implies, the reduce job is always performed after the map job. So let's take a simple example. Assume you have 5 input files. Each file contains 2 columns, a key and a value in the Hadoop terms. Each tuple represents a city and the temperature recorded in that city on a particular day. We want to find the maximum temperature for each city across all of the data. Each file has multiple readings for the same city, and different files might contain readings for each city. The MapReduce framework can break this down into 5 map tasks, where each mapper works on one of the 5 files. Each map task goes through its input data and returns the maximum temperature recorded in that file for each city. The results from the mappers are fed to the reducer. The reducer combines the map results and outputs a single value, the overall maximum for each city. A good analogy is the way a census was conducted in the Roman times. The Census Bureau would dispatch its people to each city in the empire. Each census taker in each city would be tasked to count the number of people in that city and then return the results to the capital. The results from each city would be reduced to a single count, sum of all cities, to determine the overall population of the empire. This mapping of people to cities in parallel and then combining or reducing the results to a single figure is much more efficient than sending a single person out to count every person in the empire in a serial fashion.
MapReduce. The term MapReduce actually refers to 2 separate and distinct tasks that Hadoop programs perform. The first is the map job, by a program called Mapper, which takes a set of data and converts it into another set of data, where individual elements are broken down into tuples, key or value pairs. The reduce job, by a program called Reducer, takes the output from a map as input and combines those data tuples into a smaller set of tuples. As the sequence of the name MapReduce implies, the reduce job is always performed after the map. MapReduce example 1. Assume you have 5 files, and each file contains 2 columns, a key and a value in Hadoop terms, that represent a city, and the corresponding temperature recorded in that city for the various measurement days, example, Toronto, 20. From all the data collected, we want to find the maximum temperature for each city across all of the data files. Using the MapReduce framework, we can break this down into 5 map tasks, where each mapper works on one of the 5 files, and the mapper task goes through the data and returns the maximum temperature for each city. For example, the results produced from one mapper task for the data above would look like this. Toronto, 20, Whitby, 25, New York, 22, Rome, 33. MapReduce example 2. Let's assume the other 4 mapper tasks, working on the other 4 files not shown here, produce the following intermediate results. Toronto, 18, Whitby, 27, New York, 32, Rome, 37. Toronto, 32, Whitby, 20, New York, 33, Rome, 38. Toronto, 22, Whitby, 19, New York, 20, Rome, 31. Toronto, 31, Whitby, 22, New York, 19, Rome, 30. All 5 of these output streams would be fed into the reduced tasks, which combine the input results and output a single value for each city, producing a final result set as follows. Toronto, 32, Whitby, 27, New York, 33, Rome, 38. Big data analytics is the process of examining big data to uncover hidden patterns, unknown correlations and other useful information that can be used to make better decisions. With big data analytics, we can analyze huge volumes of data that conventional analytics and business intelligence solutions can't touch. Consider that your organization could accumulate, if it hasn't already, billions of rows of data with hundreds of millions of data combinations in multiple data stores and abundant formats. High-performance analytics is necessary to process that much data in order to figure out what's important and what isn't. Benefits of big data analytics, example. Companies like Amazon and Google are masters at analyzing big data. And they use the resulting knowledge to gain a competitive advantage. Just think about Amazon's recommendation engine. The company takes all your buying history together with what it knows about you, your buying patterns, and the buying patterns of people like you to come up with some pretty good suggestions. It is a marketing machine, and its big data analytics capabilities have made it extremely successful. Big data analytics. Basic analytics. Slicing and dicing refers to breaking down your data into smaller sets of data that are easier to explore, like different views of data. Similar analysis to normal business intelligence, except we are dealing with huge volumes of data set. Basic monitoring. Monitor large volumes of data in real time. Anomaly identification. Identify anomalies, such as an event where the actual observation differs from what you expected. Advanced analytics. Predictive modeling. A predictive model is a statistical or data mining solution consisting of algorithms and techniques that can be used on both structured and unstructured to determine future outcomes. Text analytics. The process of analyzing unstructured text, extracting relevant information, and transforming it into structured information that can then be leveraged in various ways. Others may include advanced forecasting, optimization, cluster analysis for segmentation or even micro-segmentation, or affinity analysis. Operational analytics. When you operationalize analytics, you make them part of a business process. For example, statisticians at an insurance company might build a model that predicts the likelihood of a claim being fraudulent. The model, along with some decision rules, could be included in the company's claims processing system to flag claims with a high probability of fraud. Monetizing analytics. Analytics can be used to optimize your business to create better decisions and drive bottom and top line revenue. For example, credit card providers take the data they assemble to offer value-added analytics products. End of the lesson. Goodbye.